Okay, we're back to AP Chemistry. We're on podcast 3.6 now, and we're going to look at types of redox reactions and how we can use the type of reaction to predict the products. So since this is a little bit complicated, I asked for help, and I've got the Brewerton family in here. Christian and Courtney are going to help out today. Say hi, guys.
Hey.
Hi.
All right, here we go. Let's get started. We're going to look at some simple redox, and you've seen these before. Single displacement reactions are always redox reactions. So we'll have hydrogen displacement, metal displacement, and halogen displacement. And then combustion reactions are not single replacement, but they're just fun, and they're always redox. All right, so here's an example of hydrogen displacement, where the calcium metal is going to replace the hydrogen. So I'm going to rewrite water as HOH so we can see how it replaces the hydrogen. Right, this calcium is going to kick out the hydrogen, and what are you left with?
CaOH.
Right, and because of the charge of calcium here, we need two hydroxides, and of course hydrogen is Brinkelhoff, so we've got two of those, and that meant we had to have two waters to make that work. So we balanced the equation just like a normal reaction, normal single replacement reaction. So now let me clear that writing, and we'll look at metal displacement. In AP Chemistry, these reactions come up a lot in question number 4. It's the first one in part 2 of the free response questions, right? That's what they call it. So you'll always see questions like this where you have to write down what it is. In this case, it will always occur. You don't have to wonder if the zinc is more active than the copper. It is, because they never have no reaction. Okay, so what kind of copper sulfate is this? Copper 1 or copper 2?
Copper 1. It's copper 2. Yeah, it's 2. Yeah, that would be 2.
Of course. Sulfate is a -2, so the copper is a +2. And that's pretty handy because zinc is always going to be a +2. So this reaction's already balanced. We didn't have to do anything to it. That's the kind I like.
Oh yeah, those are the best.
Yeah, the ones that just automatically balance. Okay, halogen displacement always goes from activity series top to bottom on the periodic table. We know that chlorine is more active than bromine. Whoops, wrong color. Chlorine is more active than bromine because it's higher up on the periodic table. So this one's going to go. But we already knew that because I just told you there's always a reaction. You never get to put no reaction. Kind of a drag. There's always a reaction. Yeah. All right, and then because of Brinkelhoff, we of course have to balance this so that we have 2 of the chlorines, 2 of the bromines, and then this isn't balanced. 2 potassiums, right over there. Now we're balanced. I thought I had that all done. So those ones are pretty simple. Let's look at combustion. Music from my other computer. Combustion, this one's methane, right? And so this is the one you see in the Bunsen burner. What are the products of combustion for hydrocarbon?
Carbon dioxide and water.
Every single time. So my tip is to balance carbon first, and then once that's done, balance the hydrogen, and then you can take care of oxygen after it's all said and done. And this one's balanced, I think. Yep, it is. Good. We get to move on to the hard part, because if it seemed like we were going a little bit fast for that other part, we were. We got to get to the good stuff now.
Oh,
Disportionation reactions are those where one substance gets both oxidized and reduced at the same time. These ones are hard to predict because you will look at the chlorine and say, it could do this or it could do that. Well, guess what? It's doing both. So let's look at the oxidation number. For an element, it's always 0. So chlorine in its elemental form is always 0. You knew that, right? Of course. Good. Now chlorine joins up with oxygen. This is our hypochlorite anion, and it has an overall -1 charge. And then this chlorine here, minus is negative, there we go. This chlorine here has a -1 charge, and that's all there is. It's monatomic. So that oxidation number is -1. But on this side, we know that the sum of our chlorine plus our oxygen, which is a -2 every single time, their sum is -1. So this is a weird case where chlorine is not going to be negative. Anytime a halogen combines with oxygen, the halogen has a positive oxidation number. So use a little algebra here. What's the charge of the chlorine here? Let's add the 2 across.
Oh, yeah.
Plus 1.
Exactly.
There you go. So chlorine is positive 1 and negative 1. What we see is that the chlorine went from 0 to positive 1, and so that oxidation number went up. Anytime your oxidation number goes up, that's the part that is oxidized. Okay, and then the chlorine went from a 0, I should put zeros there so we know they're not oxygens, right? Went from a 0 to a negative 1 to make chloride. And that oxidation number went down. Well, it's pretty simple. It's called reduction when it goes down. That makes sense.
Yeah.
Yeah. Let's look at reactions involving oxoanions. And by oxoanions, we mean the polyatomic ions with oxygen in them, right? And here's our 2 biggest culprits, permanganate and dichromate. And you're going to get to know these guys so well. Yeah, you're just going to know. The charge of permanganate is plus 5, and the charge of chromium in dichromate is plus 7, and you'll remember that forever because you're going to use it so much.
Sweet.
Yes.
If you get potassium permanganate on your hands, it turns different colors.
Yes, right.
And it doesn't go away.
Right, because every horrible thing that could happen in the lab has happened to Courtney Brewerton. We were just having that discussion. It's all happened to him. Everything I warned you about, he did. Yeah.
Except getting stuff in my eyes. I never did that because I always wore goggles.
Okay, good plan. At least there was
I did
that.
one thing right.
Yes. All right, then let's look at what we do here with these. This one involves dichromate. And dichromate turns into the chromic ion when it's in acidic solution. And I know this one's acidic because, look, there's hydrogen ions. Acids release hydrogen ions or protons, and that's what makes them acid. All right, so now we know we're in acidic solution, and dichromate is going to turn into the chromic ion. Let's look at the oxidation numbers and see if we can figure out what thing is oxidized and what thing is reduced, because there's a lot of stuff on here. It's kind of hard to tell what's what. So let's work out chromium in the chromate. We know what oxygen is going to be, right?
Mm-hmm.
So we have an overall 2 minus charge. What's the oxidation state of oxygen?
-2.
Always -2. And then how many chromiums? We've got 2. So I'm going to use X for the charge because we don't know what it is yet. And now it's a case of simple algebra. And I'm going to write out all the steps because I say it's simple, but that's where it's easiest to make mistakes, right? With positives and negatives. Even in master's level and PhD level math classes, the most common mistake is with negative signs. We don't want to make one of those. All right, what's X?
6.
Yep. So we have a positive 6 for each of our chromium atoms here, and a positive 3 on this side. This one's not balanced, Courtney. Look, I lied. We need 2 of those. Gee, many. I thought we were balanced. We are now. I hope. We're not going to mess with it if we're not.
Yeah, we are.
No, we're not, because I did this in the last podcast. They don't need to see this one again. Let's see, iron. Let's look at iron. Goes from a +2 to a +3. All right, so we're looking for what thing's going up and what thing is going down. Iron goes from 2 to 3. That went up, so we call that oxidation. Okay, and strangely enough, that makes iron our reducing agent because it caused the reduction in something else. Mm-hmm. Right? So the thing that is oxidized is called the reducing agent. Chromium went from a 6 to a 3, and so that went down. And so that was the thing that was reduced. And the dichromate is our oxidizing agent. I can't spell oxidizing.
I didn't learn how to spell oxygen until like the last week of AP Chem.
Wow, that's
Seriously?
ridiculous.
Mm-hmm.
It's a
and
good
chlorine. I didn't know how to spell
It's
it.
a good thing you're not great on spelling in this class.
Wow.
Yeah, that's pitiful. All right, so that's just the basic types of redox reactions. The disportionation ones, you probably won't have to predict products. You'll just have to try and balance them. We'll be given more information than what we had. And for oxoanions, these are the ones that are going to show up on question number 4 in the net ionic equations. And so from here on out, Every time you have a test, you're going to get 3 questions like this, and you'll probably have one of these on there with permanganate or dichromate or chromate or some other ridiculous thing, oxalate. That's one of my
You get them
favorites.
for bell work too.
Right, bell work, because that 10 minutes of class is about the same amount of time that you should spend on free response questions in the AP exam. So we're going to get used to you having a feel for how long is 10 minutes. Bell work, yay. All right, so to predict products, you've got to have these memorized. Don't you love that, memorizing stuff for class?
Of course.
Yeah, we all do.
It's always the best.
Yeah, so my recommendation is to make a flashcard with permanganate on one side. Oops, wrong buttons. So permanganate on one side, and what it forms in acidic solution on the other side. And this should say basic solution.
And it gets easier just by looking at it almost every day.
Yes.
You get used to it.
Right.
Just kind of know it.
And that brings up a good point. In AP Chemistry, if all you ever do is the work that I assign, you're not going to get a very good grade. You have to also study. So you do the work that I assign, and then you read your book some more, and then you look over your flashcards and look back over your notes again, even though I didn't assign it, because that's what studying is. Yeah. So you're going to learn a lot of things in this class, but mainly we're going to learn how to study.
Sweet.
Yep. It'll help you later on. Okay, so wait, I wanted to show you. This is our chart for oxidizers. This is our chart of describing what's going down. If you notice your oxidation number is going down, this is the chart we look on to see what could we make here. And then the next one is our reducers. These are the ones that are going up. Oxidation number is going up, and this is what we're going to form. Okay, so this will help you predict what's going to form in a reaction. You have to have at least 2 elements changing their oxidation number, or you don't have a redox reaction. Okay, and if you have both things going up, you're doing something wrong. And it's probably a positive sign or a negative sign somewhere. All right, here's one that we can understand what happened here because we did this reaction in class. Solid copper is added to dilute nitric acid solution. Nope, I lied. We used concentrated nitric acid. This was the first step in your copper series of copper reactions that you did last year in general chemistry, only we used concentrated. So we have copper is going to turn into something. What are our choices for copper's charges? We could have a 0, but that's what it is here because it's solid copper. Or we could have a 2, or we could have a 1. Generally speaking, go with the higher charge. Okay. And then our other choice here, copper is added to dilute nitric acid. So since nitric acid is a strong acid, I'm going to leave off that proton for now. It automatically breaks apart into hydrogen and nitrate. Okay, this hydrogen is going to come back later on, but for now, we're just going to focus on this piece. Okay, that proton, he's off doing his own business. Okay, what's nitrate going to turn into? To answer this question, we got to look at our chart. So let's just go back to here. Nitrate. I've scribbled all over everything. It's hard to find. Okay, here it is. Dilute nitric acid does something different than concentrated nitric acid. Right? In concentrated, it goes to NO2, which was that brown gas that your teacher warned you not to breathe it,
Oh yeah.
or you could die. Yeah, Courtney probably breathed it.
Yeah, that was still coming out. That
really
was still
bad.
coming out of our beaker. It was still coming out of our beaker when we took it out of the hood, and we were like, "Oh my goodness!"
Yeah, back to the hood.
Yeah.
It smells pretty bad, and you feel really, really sick after.
Yes.
Same
Yeah,
with chlorine
it
gas.
smells bad.
Don't breathe it out. You'll sick for a week.
Good advice. Right. The voice of experience. All right, so we're looking at dilute nitric acid. This is not any safer. NO, nitrogen monoxide. No safer than that other brown stuff. Oh, I hate the scribbles. And I don't have an eraser on this pen. So we're just going to have a box in the way.
Sweet.
Yeah, that's handy, isn't it? All right, now we're doing that algebra stuff again. Okay, because we have a 0 overall charge for a compound. Oxygen is -2. And then that means nitrogen is +2. That part was easy. Right, now let's come to this side. Nitrate has a -1 overall charge, so we have to add up to -1. We have 3 oxygens. This isn't so bad, huh? So what's the charge of our nitrogen here?
Wouldn't that be a -1? You
Yep.
have it written.
Thank you. That's why I asked you to help me out. My proofreader. Okay, so now we've got a positive 5. Okay. So let's make sure that we're doing this correctly. If we go from 5 to 2, that's going down. Reduction. So we have to give away electrons. No, we have to gain electrons to get more negative. 3 of them, right? Okay, so if this part's going down, we expect copper to be going up. Is that what our charges show?
Yeah.
Oh, good. We must be doing something right.
Sweet.
Yes, and here's where we're giving the electrons away, right? Because we get more positive when you lose your negativity. Yes. All right, we're getting there now. So we've got our oxidation numbers. We don't need this part anymore. We just need to balance this. Sounds simple, right?
Mm-hmm.
Sure. Well, first we're going to balance everything that's not oxygen. So copper is balanced. Nitrogen is balanced. Hey, done. It was easy.
I told you.
Yeah. Next up,
Your
balance.
electrons aren't, though.
Nope, not yet. We'll take care of that at the end. Let's balance oxygen next. Okay, I have 3 here and 1 here. So do you remember how to balance oxygen?
3.
I need to have 3, so I need 2 more. But we're going to always add water to
Ah.
balance oxygen.
All right.
Yeah, you haven't seen that podcast yet.
No,
you didn't know that.
not yet.
Oh,
Yeah.
I probably should have answered.
Yeah.
Well, that's okay.
That's why you're here.
Yeah. Okay, so now we have 3 oxygens on this side and 3 oxygens on this side. But by adding water, we messed up our law of conservation of mass because we didn't just add oxygen. We added hydrogens too. So how many hydrogen ions do we have in this mess?
4.
Right. So we're going to add 4 hydrogen ions. Remember up here I told you they'd come back? There they
Yeah.
are. Yep. Because we're in acidic conditions, we get to keep them there. And now we got to take care of those electrons. Yeah, Courtney?
Mhm.
All right. So I got to get electrons to be equal. I have 3 and I have 2. So we'll use the least common multiple and multiply our copper by 3 and our nitrate reaction by 2. Okay, so I'm just going to clear this screen. I can't clear the screen, then we won't know what we're doing. I'm just going to rewrite it down at the bottom with my pen that I like. Okay, so 3 coppers, capital C, made 3 copper ions and 6 electrons. Right? So far, so good?
Mm-hmm.
All right, good. You do the math on the next one. How many hydrogens?
8.
Okay. And how many nitrates?
2.
How many electrons?
6.
Keep going.
2.
2 nitrogen monoxides.
And 4 waters.
All right. Good. It's getting easier all the time. Okay, now I have electrons on this side that balance the electrons on that side. Just like with your Hess's law reactions, something that shows up on both sides of the equation will just cancel out. And that's why we made them the same, so we could cancel them all out. What you gain has to be equal to what you lose. So our next step is to add our 2 half reactions together, and now we do need more space. I don't know, all right. We're just going to have to write it right up here. So we have 8 hydrogen ions, 3 copper atoms, 2 nitrate ions. Our electrons are gone. So is that it for reactants? Yep. Okay, good. And then we made 3 copper ions. Those would be cupric ions, right? Because it's the higher charge.
Mm-hmm.
2 nitrogen monoxides and 4 waters. And that's how you balance a redox reaction. You have to break it apart into the half reactions first. And we used our little chart of what goes up and what goes down to predict the products. Piece of cake?
Sure.
Not really.
Yeah.
But if you follow the same steps every time, you'll
You
get
get
there.
used to it.
It doesn't get better. You just get used to it. All right. Ethanol. You probably haven't learned how to name organic compounds yet because that's your fall break assignment. So ethanol is the kind of carbon that has 2 carbons and 5 hydrogens, and then an OH group to make it an alcohol. We're going to burn it in air, so of course it's not reacting with the nitrogen, just the oxygen. All right, every combustion reaction of hydrocarbons makes the same thing.
Yeah, CO2, H2O.
Right. Okay, well this one should be easy to balance, right? And we could do all the oxidation numbers and all that mess, but we've recognized this is a combustion reaction, so it would be a complete waste of time for you to do balancing by figuring out what's oxidized and what's reduced. Okay, because look, we added oxygen and took oxygen away, so it's kind of a mess. So now we're going to balance the carbons, too. And then we're going to balance the hydrogens. I have 6 total, so I need 3 waters. Now count up your oxygens. I have 4 here and 3 there, for a total of 7. All right, so I have 1 over here. How many O2s do I need?
3.
Yeah. Got to add up to like 6 here and 1 there. So we're done. We balanced it.
Yay.
Yeah, we don't have to have
Just
hydrogen
always-
ions and all that
Always
junk.
balance oxygen last.
Right. If you keep the oxygen for last, it works out a lot better. Okay, let's look at adding sodium metal to water. And based on what you know about how metals react with water, you should already have an idea what the products will be. Sodium is an element, so it has a 0 charge. And what's it going to do? It's probably going to turn into an ion. This is the only ion sodium ever forms.
Plus
Right.
1.
Yep, +1. I'll put a 1 there if that makes you happy.
Oh, okay.
Alrighty, there you go. And then we've got water. And I'm going to write it this way on purpose. Okay, because then you can see this is a hydrogen displacement problem, right? So we're going to get hydrogen ions that separate from hydroxide ions. And we can't have these guys just floating around. So hydrogen doesn't exist as a monatomic beast anyway. So we're going to take our sodium, put it with our water, and we can make sodium hydroxide here. Since this is a strong base, are we allowed to write it in molecular form? No. Courtney's shaking his head because he knows. You better not. So we have to ionize this, and then our hydrogen was left alone. Hydrogen alone always is diatomic. All right, so if you kick out the hydrogen, you got to have 2 of them. All right, so we're not balanced because this is 1 hydrogen. We need 2 of these, and that means we'll form 2 of these, and I need 2 of these. Now the only thing we need to fix is right here. 2 sodium hydroxides we must always write in ionized form. That breaks apart into 2 sodiums and 2 hydroxides because it's a strong base, so it always breaks apart. I think that's it. We don't have anything else that we have to ionize because this is molecular and that's atomic, so we're good. Balanced. Moving on. Oh, it's a peroxide problem. Okay. All right, let's look at hydrogen peroxide added to a solution of iron 2 sulfate. Okay, so I have this worked out, but I can see in the work that I did, I messed this up the last time. So we're not going to look at that. We're going to start fresh and do it right this time. So peroxide is this anion. It's O2 with a 2- charge. So we are going to need 2 hydrogens to go with it. H2O2 is hydrogen peroxide. And we're going to add it to a solution of iron 2 sulfate. Do you remember your solubility rules?
Not really.
Okay, so in your summer assignment, you're required to memorize those. You've got a little ways to go yet.
Yeah.
All right, that's okay. Summer's not over yet.
I'm working on
Yeah,
it.
summer's not over yet. But we learned these rules that we call knock-o-no-so. And these rules help us remember what's soluble. Sulfates are all soluble except for 6 of them. And it's silver, mercury, lead, barium, strontium, and calcium. Notice I didn't mention iron. So it's not an exception. This is always soluble. Since it's always soluble, that makes it a strong electrolyte, and sulfate is going to be a spectator here. So I'm going to leave him out. All right, so now we need to know what's going to happen. Peroxide is a weirdo. It can do a couple of different things. So I'm going to take us to the handout that you have in your little packet. It's hiding. Yep, peroxide is down here. So let's get it where we can see it. Here's our peroxide, and it could turn into oxygen. That's one thing that peroxide could do. But peroxide's a weirdo. It could also be down here. Yeah, that's not supposed to be oxygen in both places. One is water, one is oxygen. And in this case, I don't know what it's going to do. We're going to have to see what the iron does, and then that will tell us what to do with our peroxide. Okay, do we have any hints about whether or not we're in acidic solution or basic solution? Let's look. Oops. Here's our problem, and it doesn't say. When it doesn't tell us, we assume we're in acidic solution. If we're in basic solution, they will tell us. So always follow the rule, because if there's an exception to the rule, they're going to tell you it's an exception. Since we're in acidic solution, let's look at iron in acidic solution. Actually, we don't have to look, because our only options are to go to 0 or to go to a 3. Iron's oxidation states are 0, 2, and 3. We never go to a metal, to the elemental form. We just don't. So we already know. Oxygen is going to do a +3, and so that's going up. All right. That means peroxide has to go down.
Mm-hmm.
Okay. Well, which one was going down? We said we could make oxygen, which is a 0, or we could make water, which is H2O. So the oxygen here is a -2. Oxygen here is a 0. What is oxygen in peroxide? O2 with a 2- charge means that each oxygen is a -1 oxidation number.
Mm-hmm.
All right, so we're trying to go down. What's less than -1? 0 or -2?
-2.
Right. So because we know what happened to iron, that helps us figure out what to do with peroxide. All right, well that was a little bit crazy. Let's do the electrons. Well, we got that fresh in our mind. Every oxygen gained another electron, right? And how many oxygens did we have? 2. So we're going to have 2 electrons gained. And on this side, to go from 2 to 3, we had to give away 1 electron.
Mm-hmm.
All right, now we're getting somewhere. We're going to balance everything that's not oxygen first. So that would be hydrogen. Okay, done. Okay, and then iron, done. Balanced. Now we have to balance oxygen. I had 2 oxygens here, and I have 1 oxygen here. I need another one. So let's have another water. That's how we balance oxygen, by adding water. And now I've got to add hydrogen ions to the other side.
Mm-hmm.
Let's add 2 of them, because if I added 4 of them, I wouldn't be balanced anymore. Right? I already balanced hydrogen. Now I'm balancing the ones that come from the water. And I think that's it for those hydrogens. Now we have to make sure electrons are equal. So I'm going to have to multiply this entire reaction by 2 to make the electrons the same. So 2 ferrous ions gives us 2 ferric ions, whoops, a 3+, and 2 electrons. So now we're going to add our half reactions together and we'll be balanced. You guys are going to make sure I don't forget anything, right?
Yeah.
Okay, good. Peroxide, electrons canceled. How about we do 2 of those?
Yeah.
Yeah, good. Then I have 2 waters. Can I just write them together?
Mm-hmm.
Let's do that. And then 2 ferric ions, and we're done. We've balanced that entire reaction. Okay, so now let's suppose that you decided to do something different. Suppose that you were a very creative chemist and you did make the free metal Fe with a 0, and then you turn this into O2 with a 0.
Mhm.
Okay? Then are you going to lose all your credit here? Because you did it wrong.
Yeah.
Yeah, probably not, actually. You're going to lose 1 point for predicting the wrong products. But if you can balance that, you're going to get the point for balancing.
Yeah, if you
Sweet.
balance it and get the reactants that fit what you put down, you still get most of the points.
Right. So even if you guessed wrong in predicting the products, be consistent in the rest of your work and you'll get the credit for that part. So at least if you don't know what to do something, because you just might accidentally get points. Hey, that's it. When it goes to this screen, that means podcast is over.
And just
Sweet.
make sure on the AP test you decide to answer more than 20 questions.
Yeah, right. That happened one year. One kid answered 20 multiple choice questions.
He thought he'd get 100%,
And there
Yeah.
are how many?
like 100.
75.
Oh,
Yeah,
So-
Okay.
bad decision.
that's a bad idea.
All right, well, you guys go enjoy your summer.
All right,
Thanks
sweet.
for your help.
Thanks.